recording. Okay, in our last lecture, we saw the operator norm for a linear transformation. So if we have T mapping from Rn to Rm, then we define the operator norm of T. Now, we defined it as an infimum, but then our major result of the last lecture was that we could write it as a supremum. I'm going to write it as that supremum here. It was the supremum of the 2 norm of its images on the unit sphere. Okay. Now, linear transformations are the same exact thing as matrices. So we can extend this norm to matrices. So given an M by N real matrix A, we define the operator norm of A to be the operator norm of the associated linear transformation. So this is LA from Rn to Rm defined by LA of X equals less multiplication by A. Okay. Now, all of our results from the previous section translate to this context. Or from our previous lecture, translate to this context. So for linear transformations, I guess this is a result that we should have said last lecture. I don't know that we actually did. So if you want to bound the 2 norm of T of X, that is at most the operator norm of T times the 2 norm of X. Okay. That's really the definition of what the operator norm is attempting to capture, is how much do you stretch vectors. Okay. Now, I'll just point this out because if you've had a course in linear algebra, you might be thinking this. This is very strongly related to eigenvalues. I'm not sure if you defined this, but in linear algebra, you have the spectral radius of a matrix is the absolute value of the largest eigenvalue. Now, when we're dealing, well, I guess I should, sorry, I got ahead of myself here. I should talk about matrices. Okay. So the point I was supposed to make first is this exact same thing holds for matrices. We have a bound on the 2 norm of AX given by the product of the operator norm on A and the 2 norm on X. Okay, now, as long as we've got a real matrix, this is the spectral radius of the matrix. Okay? We're not going to use that. Okay. Oh, I'm sorry. As long as we've got a real square matrix, then this is the spectral radius. Otherwise, we can define it in terms of singular values. But anyway, we're not going to get into that. We're just going to use this. We're not going to do any more linear algebra than we have to. So we're just going to use it as it is here. Okay. Notice that we also have, this works nicely with matrix multiplication because if we want to bound the 2 norm of ABX, okay, now let's just, let's assume these matrices and vectors are appropriately sized, because otherwise this doesn't make sense. But this would be the operator norm of A. Sorry, at most the operator norm of A times the 2 norm of B. Well, that would be at most the operator norm of A times the operator norm of B times the 2 norm of X. Okay. And now you can look at this and you can say, what that means is that the operator norm of AB is at most the product there's a word for this. This is submultiplicativity. That inequality won't in general be an equality, because you can imagine that the vectors that B stretches out are not the same as the vectors that A stretches out, so when you combine the two, you do AB, you might not be getting the maximum stretching factor that each of them individually would get, okay? Any questions so far?
So, to this point, we've only looked at operators that are going from an Rn to an Rm, but just looking forward, like the derivative and integral are linear operators. So when we, how do we translate to a different domain? Because I imagine this would be really useful in those sorts of contexts. So I know you could probably do polynomials easily, but, sorts of other functions may not have a nice mapping to an Rn space domain thing.
I'm a little bit confused about what you're asking about. So is it you want to generalize the operator norm, or
yeah,
you want to...
I'd want to generalize the operator norm, like going from a space of polynomials to polynomials. Like that one,
mm-hmm.
you can do easily because you can do polynomials to Rn, but
right.
Sort of just like a general, like, my linear transformation can take a function and spit out another function, like the derivative.
Okay, so our operator norm is defined this way. I mean, we could define it this way because we proved it's the same thing as that. You could extend that definition to nonlinear transformations. Your problem is it's not going to do what you want it to do. So what we're actually going to see when we take the derivative, okay? And this is kind of the big change from regular Calc 3 to us doing multivariable calculus here. In regular Calc 3, you think about partial derivatives, which are just, they're essentially single variable functions, okay? In this class, we're gonna focus more on the total derivative, or just the derivative is what we're gonna call it, which is a linear approximation to your multivariable function at a point, okay? It's going to be a linear approximation, though. And because it's a linear approximation, we're going to be able to treat the derivative as one of these linear transformations. Okay, I don't know if that helps clarify at all.
I think it does. I'm sort of piecing it together, but I'm sure we'll get there and make more sense later.
Yeah, I mean, so in some sense, like the whole, all of calculus is just approximating functions by linear functions. And so we're doing all this build-up in the linear algebra so that when it comes to approximating more interesting functions by linear functions, we've got all the machinery we need to deal with the linear function approximations. Okay. I mean, I hope it'll make a lot more sense when we get to it, which should be next week. Actually, I guess Monday and Friday of next week, we'll be doing derivatives. Okay.
I have another question, just like real quick. Is this like OP norm on a matrix? Because I think I saw once something that's called an induced norm on a matrix.
Yep.
Is it the same thing or?
Okay, so we're calling it the operator norm. It's also called a matrix norm. And it is, you also sometimes see it as the norm induced by a vector norm. Okay. Now, we developed all the theory where, if you go back to the previous lecture, you can take any norm on your vector space and you can induce an operator norm that agrees with that vector norm. But then, in the previous lecture, right before we created our operator norm, we said, never mind this generality. Let's just fix the 2 norm. So all the stuff we're going to do is for the 2 norm. Okay. But you could do it with any norm.
Okay, thank you.
Of course. Okay, so our big topic today is inverses. I'm going to, in just a second, quote a theorem from linear algebra. Let's just kind of get our head in the right place. If we want to think about inverses of, let's let A be an m by n real matrix. Okay, and this corresponds to our linear transformation, LA from Rn to Rm. Okay. Now, A is invertible. And what do we mean? As a matrix. Okay. So that statement is happening in the ring of matrices. We're saying that the matrix A has a multiplicative inverse there. This is happening if and only if LA is invertible. As a function. Okay, that invertibility is happening in kind of the more familiar space of just functions. When do functions have inverses? Okay. Now, well, when do functions have inverses? Let me ask that question to you.
They need to be bijective.
Huh? They need to be onto and 1-to-1. Right? And we go up here and we look. Our linear transformation, LA, is mapping from Rn to Rm. Let's see. How would it be onto? If m is greater than n, then onto is impossible. Okay. And if you're 1-to-1, if let's see, if this dimension of your range, of your codomain is smaller than the dimension of your domain, then this is impossible. Okay, and I know you all know this conclusion already, but that would be the way in this class to see if a matrix is going to be invertible, it has to be square. Okay. Now, we all know that's not quite enough, right? Not all square matrices are invertible. What does it take? Well, how about I do it this way? I'll state the result. Proposition. For an n by n real matrix A, the following are equivalent. Okay, meaning that if one of them holds, then they all hold. Okay. What are equivalent conditions to invertibility? For a square matrix.
The determinant is non-zero.
Mm-hmm. There's more though.
The rank is said.
Mm-hmm. I like just calling that full rank. There's a lot more. You can keep going. I mean, you know, some of these you'll argue that they're very, very similar to other ones on the list, but one is just that linear transformation is 1-to-1. Okay, because it's a theorem from linear algebra that if it's 1-to-1, then it's also onto. And another one is that it's onto. It's a theorem that if it's onto, then it's 1-to-1. Anybody else?
If it's full ring, doesn't the null space have to be 0?
Mm-hmm. Very good. That's what I was just about to write. The null space of A is just the 0 vector. Okay. You know, like that one's also pretty obviously equivalent to being 1-to-1. Because if you took two things, if they were the same, then their difference would map to 0. So, okay. Let's stop there, but we could go on, right? In the lecture notes, I've also got that it has a left inverse, which means that there's a matrix B so that B times A is the identity, or it has a right inverse. Okay, so having a left inverse actually means you have a right inverse and vice versa. Usually when we say invertible, we mean you have both a left and a right inverse, but it only takes one. Okay, and these two correspond in some way to those two. But I won't put myself on the spot right now and tell you which one goes to which one. Okay. So that's our very brief review of invertibility for matrices. Now, let's prove some analysis things about this. Okay. I'll tell you the result we're getting to, which is, I think, a really neat result, okay? If you take, well, first of all, if we take the space of n by n matrices, we have a metric on it. We can put the metric induced by the operator norm on that space. Okay, so we could look, oops, we call it, okay, we could look at the n by n matrices with the operator norm, where the operator norm between A and H, and this is the norm induced by, oh, sorry, the operator metric. The operator metric is the metric induced by the operator norm. So it's the operator norm of the difference. Okay. Okay. This is a metric space. Okay. Our big result today, we have two results. Our big one, which we probably won't get to the proof of it, but hopefully we'll be able to hint at it. Our big one says, in this metric space, the set of invertible matrices is open. Okay. So that means if you take any invertible matrix, there is some little neighborhood around it where any other matrix in that neighborhood is still invertible. Okay, or you could change the entries by a little bit and you'll still be invertible. Okay, the second part of the big result says that the function that takes a matrix to its inverse is a continuous function with respect to this metric, with respect to the operator metric. Okay. I mean, so actually that, that's saying a very similar thing, okay? If you perturb, I mean, that's actually saying something a little bit stronger. That's saying if you perturb the matrix by a little bit, not only will it stay invertible, but its inverse will stay very close to the inverse of the original. Okay? Now, like I said, we'll see if we get to that. To prove that, we're going to need the following results. And we're going to spend most of our time proving this lemma, because I think there are a lot of good good uses of the stuff we developed in this lemma, and it's a good way to get a feeling for what proofs are like in this area. If A is an n by n matrix and its operator norm is less than 1, then if you take the identity minus A, that's invertible. Moreover, once we know it's invertible, the operator norm of its inverse is at most 1 over 1 minus the operator norm of A. Second. Okay, are there any questions about that before we start proving it?
So we're just getting inverse of the thing we said was invertible.
Yeah, so the first part says it's invertible, the second part gives a bound on its operator norm.
Okay.
Does this remind you of anything?
The geometric series a little bit.
Yeah. And if you think about it, this, over here on the left, the matrix, is sort of a geometric series of matrices. Okay? Now you can make that rigorous, but we're not going to make that rigorous. Okay, we'll ignore that interesting connection. And we'll just prove this thing. Okay. First thing is we need it to be invertible. Okay, let's look at, okay, we just stated this theorem about how the following things are all equivalent to invertibility. The one we're going to use is that the null space is 0. So we're just going to argue that it can't send anything non-zero to 0. Okay, so let's let x in Rn be arbitrary. We'll argue that the only way it could be 0 is if it started out, sorry, the only way it could be mapped to 0 is if it started out as 0. Okay. So let's look at the thing we'd like to show is invertible times x. Okay. Now, again, we want to say this can only be 0 if x was already 0. So it would suffice to consider the 2 norm. If we can show the 2 norm can only be 0 when x is already 0, then that's good enough. Okay, now let's play around. Let's expand the inside here. That's just x minus ax, right? Okay, remember this is just the 2 norm on vectors here. 2 norm on vectors satisfies the triangle inequality. So we want the lower bound version of the triangle inequality. Okay. If you've got, here we've got one vector, it's x, minus another vector, which is ax. The smallest that difference could be is if x points in one direction and ax points, well, I guess in this case, ax points in the same direction so that when we subtract it, we go backwards towards the origin. Okay? But still, our result would have to have length at least the norm of x minus the norm of ax. Okay, that's the smallest we could possibly have it be. Okay. Now,
Why do we not need an absolute value on that?
Okay. So think about it. The absolute value only makes the inequality, it makes the inequality better. So by not putting the absolute value on it, we're making the inequality worse, which we are allowed to do.
Okay, that makes sense.
Right? We're actually giving up something. And the reason we're giving it up is actually, you look at our hypothesis, and we're going to use this right now. But you look at that hypothesis, the operator norm of A is less than 1. So we actually know that AX is going to be smaller than X. So another way to think about it is we know which side of the absolute value we're on. Okay?
Okay, thanks.
But we're always free to give up the absolute value. We just might not get what we want. Okay. And this is exactly what I'm going to say right here. We know that the 2 norm of AX is at most the operator norm of A times the 2 norm of X. Okay. So now if we make that negative, we'll do that over here. We can, that's a lower bound on negative 2 norm of AX. Okay, and now we might as well just factor out the 1 minus operator norm of A. There we go. Okay, what's our conclusion? If in minus a times x is 0, then x was 0 to start with. Okay, because the only way that thing could be 0 is if its 2 norm is 0. But we have a lower bound on the 2 norm, and this thing right here is positive. Okay, so that means we're invertible. That's the first half of the results. Okay, now, what about the upper bound on the operator norm of its inverse? Well, again, this stuff might feel a little foreign. That's just because we haven't done that much, analysis with linear algebra yet. But these are really kind of all the standard things. So given any vector, the inequality above, we're just going to play with that. Shows that. Let's see. Does it really? Yes, it does. We're going to look at that. Okay. Oh, I'm sorry. We're going to do a trick first. Our trick is we're going to multiply by this thing. Hold on. I got ahead of myself above right before. There we go. There's just one of these stupid tricks. We're going to multiply by I minus A times its inverse. And now we're going to think about it grouped that way. And then I lied about what we're going to use in the above. What we're going to use in the above is just this part. Okay. The x has changed. But what does this say? This says that the 2 norm of I minus a times some vector is at least this thing times the 2 norm of that vector. Well, we can apply that here. This is at least that thing, 1 minus the operator norm of A, okay, times the 2 norm of this stuff okay? And that's actually what we needed to show. Okay, you might not see it yet. Let's rewrite it. In other words, for any x in Rn, we have, let's solve for this one. We have this. How did I get that? I solved for that right there. Okay, and this gives it to us. This implies that the operator norm, oops, that was a 2 norm there. The operator norm of In minus A is at most 1 over 1 minus the operator norm of A. Now the last line follows from, well, either definition of the operator norm, but I think with the soup version that we stated at the beginning of class makes it easiest to see. So where were we? Where was that? All the way back here. If we look at the soup of the 2 norms of the things in the unit sphere. Okay, so for anything in the unit sphere, I'm going to look at this equation that I've put in red here. If x is on the unit sphere, then this part is, its 2 norm is going to be 1, and our norm is going to be, the 2 norm is going to be at most 1 over 1 minus the operator norm of A. And, okay, so that's an upper bound on the soup. And therefore, the soup is at most that. Sorry, it's an upper bound on everything in the set, and therefore the soup is at most that. Okay, with our last 10 minutes, are there any questions before we go on? Case are big results. For every value of n, the set, yeah, let's give it a name. In of invertible n by n matrices is an open subset of this metric space of n by n matrices with the operator metric. Moreover, the mapping F which would map from the invertible matrices to themselves, defined by F of A equals A inverse, is continuous with respect to this metric. Now, we proved a couple lectures ago that all norms are equivalent, and we've noted that these matrix spaces can be viewed as vector spaces. So actually, this is true for any metric. We can replace this operator metric, okay, with any metric that's coming from a norm, and it'll be the same thing. So the set of invertible matrices is also an open subset of the space of n by n matrices with the Frobenius metric. Okay, remember the Frobenius metric was what we got when we actually just did the 2 norm on the matrix. Right, it's the square root of the sum of the squares of the entries in the matrix. Okay, or we could do the 1 norm on the matrix or the infinity norm on the matrix, okay? It's open with respect to any of those things. But it's easiest to prove this with the operator metric. Okay? Any questions before we jump into the proof?
Yes. So is it true only for the operator matrix, or are there some other matrix are there some other metrics that that will satisfy this? Because I guess the discrete metric will probably satisfy this as well, right?
Okay, so right, by the equivalence of norms, this is true for any metric induced by any norm.
Mm-hmm.
The discrete metric isn't induced by a norm, but it in the discrete metric every set is open, so it's still true there.
Oh, okay.
Okay. I think, but I don't know, that you could come up with a metric where it's false. We're certainly not going to prove it for every metric that you could put on the space. That said, no one would ever put those metrics on the space. So, in practice, it's always an open set.
Okay.
Because you're always, when you're dealing with matrices, you're always at least in a metric induced by a norm. If you're not, frequently you're only talking about this operator metric, but okay. Okay, so let's see how far we can get in this proof. I think I can show you the trick. So what do we do to show a set's open? We take an arbitrary point, and we find a neighborhood. Okay. Okay, the epsilon I'm going to take here. Okay, obviously this isn't something you see beforehand. You see it in the proof, but we're going to take it to be 1 over twice the operator norm of the inverse of A. Okay, now we want to take something in this the ball of radius epsilon centered at A. So really what we want to do is we want to take a small thing. We want to take a matrix of operator norm less than epsilon and consider A plus that thing. So suppose that H, which is also a matrix, satisfies that its operator norm is less than epsilon. Okay, now some unmotivated stuff. Well, okay. We have, maybe I can try and motivate it. A plus H, this is the thing we want to show is still invertible. This is A plus a little perturbation. We can factor out an A, and we would be left with the identity plus A inverse H. Okay. Now, we want to show that A plus H is invertible. Why is that true? Well,
If it were invertible, then it'd be in our set, right?
so we want, here's what we wanted. We wanted A plus H invertible. So we want A times I plus A inverse H invertible. Okay? Now, A is already invertible. So really we want A inverse H to be invertible. Oh, sorry, we want I plus A inverse H to be invertible. Our previous result says that that will be true if the operator norm of minus A inverse H is less than 1. Okay, everybody okay on that? So we want, go
Are
ahead.
we stealing that the product of invertible matrices are invertible?
Yeah, I mean, it's composition of invertible functions, so it's obvious, right?
Okay.
If we look at it as linear transformations, it's obvious, I would claim. Okay, so like we said, this is invertible, and this is invertible. Oops, this whole thing is invertible if the operator norm of, I guess I'll put a minus in there, but it doesn't matter, less than 1. Okay, now notice. What can we say about the operator norm of minus A inverse H? Well, the negative sign doesn't matter. We already said we can do the product here. We can do an inequality on the product. So remove the product of the operator norm of A inverse. Well, and then this is what we defined, right? This is, let's see, less than Okay. So A plus H is invertible by our previous result. Okay. Now, that's not the end. Sadly, we're out of time. So we've proven that it's an open set. What we haven't proven is that the inverse map, the map that inverts matrices, is a continuous map between metric spaces, metric spaces of matrices. Okay, that takes a little bit more hacking around with inequalities. You should definitely read it in the lecture notes, which I will be posting later on today. And otherwise, have a great weekend, and I will see you on Monday. Bye-bye.